Okay, so now this time, apologies for the out of ordering, we actually do have Diego from DECTRIS talking about challenges for data packaging of data from their detectors. Thank you.
So yeah, as mentioned, I will be giving the first part of the presentation. Max will then take over in the second part. So first, a quick overview over some edge cases and our performance sets from our portfolio. Then a quick look at the software architecture. How does it look like? How's it built? And what do we do with the data? How we handle it? Some challenges and issues we ran into while doing it. And yeah, basically, what's the outlook for the future? What we like to see? And maybe also where can we help? I think this topic was brought up. Collaboration certainly is a possibility. And we're very interested into that. And then, yeah, Max will give an overview about future prospects. So first, a quick look at performance stats. On the left side, we have our, let's say, flagship Tiger 2 XE. It has continuous frame rate of 560 Hertz, which translates into roughly 160 gigabits per second, which is raw data in UDP. We have two different output pipelines, like the file writer, which writes the HDF5 files, but also stream. As you can see, the performance is a bit different here. So with the latest improvements we did, we reach roughly 35 gigabits with the HDF5 library, and with our stream, which is built upon the CRAMQ library, basically, we have roughly half the compressed raw data that we can send out. On the right side, you see our smallest detector that we basically have. Difference is data rate in is only 10 gigabits. However, everything is coming in quite fast with 120 kilohertz, also continuous. There, obviously, we don't have, or not obviously, but we don't really have issues whether we use the stream interface or file writer using HDF5, which is quite nice. So, software architecture, just a rough overview. I won't lose much time on this. Basically, we have a detector control unit, which is just a fancy name for a server. The operating system is Fedora, and we have basically three main components. Our software architecture is built. It's the app detector, which is basically serving the API to control the system, as the hardware drivers in it, and also all the data processing and the interface to the outside of the different data interfaces. The app calibration is basically just the calibration data and configuration settings for the modules, ASICs, and so on. And the base system is just simply serving a simple web UI to manage applications that are installed, but also server configuration and everything that's necessary, network settings, and so on. So having a closer look at the app detector, which is probably the interesting part here, which is mainly image pipeline and image mux. I will explain a bit more about this in a later slide. So the app detector is kind of built, or we have sub-modules, which is DIQ, handling all the API stuff, control services, and configurations for our detectors. Then the hardware access is basically just an abstraction to our drivers, because we have so many different detectors, hardware as boards, different hardware, and so this is basically the abstraction layer to whatever is connected to the software. And image pipeline and DIQ basically stays the same for all the detectors that we have. The image pipeline, then we do the corrections and compressions, and image mux is just a multiplexer for the different data interfaces. So monitor, which just serves TIFF at a very low frame rate. Then file writer, as mentioned before, roughly maximum 35 gigabits per second. And stream, where we serve the JSON or CBOR through CRAMQ with roughly 75 gigabits per second. If you're wondering, the gRPC is just a communication layer. So the data obviously isn't served through gRPC between image pipeline and image mux. Exactly, data handling. So what do we do in the image pipeline? First, we have the receiver receive the UDP packets with pixel intensities. This is then in one go basically count rate corrected if the correction is enabled, placed into the final position of the total image, and then also summed if this is enabled. Later on, we do a virtual pixel correction. This is based on some physical properties of the modules that we have in our detectors. So the edges of the ASIC are a bit larger, therefore this is basically then with the sensor, which is kind of glued on top of the ASIC, is rectified. So we have some larger edge pixels which are then distributed into virtual pixels. This is then an image you can see from one module, for example. Left side you see uncorrected image just with the standard configuration for each pixel applied, and on the right side then with the flat field correction. So this is just a multiplicative operation of correction value for each pixel. And then yeah, we also have a pixel mask, so for dead pixels, noisy pixels, or whatever. And this is applied in this step. Afterwards, we have compression, and you give the data further to the image mux. As we heard before, mainly Bischoff LZ4 and LZ4 are used currently. We're open for other compression standards, but I think we need kind of an agreement from the community or communities which standards compressions they want to use. And yeah, this is then moved ahead forward to monitor FileWriter and stream as mentioned. I only will be talking about FileWriter since that's where we use HDF5. So basically, with the flagship detector, we had kind of the issue that we didn't reach the required data rates. So we have an image pipeline with a max load, as mentioned before, roughly 75 gigabits per second, and with a realistic compression rate from data sets that we analyzed, which are publicly available, we should at least have a 25% compression compared to the original raw data. So this then translates to roughly 40 gigabits per second. Some prerequisites as well. The data is only always ever in RAM, so we never put this on disk, which would be way too slow. Probably everybody knows. And yeah, also the common issue that the writer itself is not fast enough. So there are some new additions to HDF, which are virtual data sets. However, it's not really optimal for us to use it due to downside also in the post-processing, which is a very important point. For us, it would maybe nice just to simulate parallel writing of a data set and just distributing it in multiple data sets. However, this then causes issues later on. And yeah, as mentioned, there's no real possibility from the standard library to parallelize writing into a single data file. So what did we do? We basically used the functionality of writing a file driver, which is given to us by the standard HDF library. We kind of also thought about just writing our own implementation of HDF5, but due to maintenance reasons, we didn't really want to do that. So file driver is a nice compromise because we can still have all the standard functions which we love the HDF library for, and just can touch basically where we have the most issues. So what we did is for FileWriter, we specified a specific tempfs using huge pages. Then, as mentioned, defined our own file driver to parallelize writing our images. As you can see on the right, we basically are using mmap and memcopy to further optimize the performance. And this we only do for chunks that are bigger than 1 megabyte. So, but since anyway we have the most issues with the 16M detector, this is kind of mostly for the bigger detectors is this being used. So the chunks are obviously not exactly like in the drawing, it's more for, so you see how exactly it looks like. Basically read the chunks directly from the image, use mmap and mcopy, and then write it in the data file. It's not necessarily that a real parallel writing, but it speeds up the writing of smaller chunks directly in the data file compared to only having a big single image that we write into that. So yeah, as mentioned, this only works because we work in RAM, but I guess that's kind of the standard anyway, dealing with this amount of data at this speed. So still, we use the virtual data set, but mainly to link like metadata or have like proper links. Since we use the NXMX standard, you can also define just file links to like data files, metadata files, and so on. But there we basically have a virtual data set to have a nice representation in the master file, where you can then directly see all the data in there without having to navigate through links or anything else. Yet this also means the data handling remains the same from the customer's perspective, which was kind of our highest priority, because as you know, every time you touch something, people need to change it, especially there are quite a lot of processing pipelines, which is yeah, nobody likes to see that, I guess. Then some future challenges. As mentioned, we kind of omitted or didn't really go further into virtual data sets for other solutions. So we saw like different options what we could do, like quadrant-wise, because anyway, for the larger detectors, we have different readout ports. For example, for the 6M, 4 readout ports. One example was just treated as a single 4M detector, for example, instead of a 16M. But then after discussion with also the community, we dropped this idea again, because usually the data is read in rows, which is then option B, obviously. We could store the data in a row representation, but then again, you come into a discussion, how big should the chunks be of a single row? How much data do you need in there to actually analyze anything? So we haven't fully dropped this idea, but this needs a lot of more discussion. And with the current state that we're having, we certainly also look into this solution a bit more. But then we have all other issues again, like if you have one image split over 20 data files, for example, then the delay between generating the image and receiving it as a customer in order to download it just gets longer as well. Then yeah, as mentioned before, post-processing pipelines are highly dependable on how the data is written. So we are very interested in collaborating with people that are also writing post-processing data pipelines. Then we will see some changes in the data rate. We expect roughly an increase of a factor 5. I mean, this opens then the question, how do we deal with data at 200 gigabits per second of compressed data, I need to say. So this is roughly 800 gigabits of raw data using HDF in the future. And do we even have to? But this is Max then going to show you what other solutions are there. And yeah, as mentioned as well, maintenance of a specific solution is really not desired. So we're really looking forward to getting a solution that works for everybody. Thanks, and I give the word to Max.
Yeah, thank you, Diego. I think I have about, 8 minutes or so. So I think Diego gave a very nice overview of what we're currently dealing with and the challenges we are already seeing, and really let's say the daunting part about this is that it really doesn't stop there, right? So if you look back what we did about 15 years ago, we had about 140 megabytes of data output from one of our first Pilatus detectors, and this really massively increased now to, Diego mentioned it, somewhere in the order of, depending on the compression ratios, 20 gigabytes or more per second. And this will really continue. So we already see detectors now being used that are factor 5 or so higher in these data rates. And obviously the question that we always ask is, okay, you should deal with this upstream in the pixel, in the detector as close as possible. I'll show you an example why this may work and why this may not work. Yeah. One of the edge cases that Diego was mentioning in the beginning is a new ASIC development that we did, very tailored towards high frame rates. And what we do here is, this is a single ASIC, only 2 by 2 centimeters. We have included pixel binning, which is obviously a low-hanging fruit to reduce the amount of data that you generate. And we've also included 8-bit floating point compression scheme inside the pixel. So you would assume that, now you have half the pixel size, so you reduce the number of pixels that you read out by a factor of 4. You also reduce the bit depth, so obviously you generated less data, right? Well, that's actually not true, because if you have the data bandwidth, you just read out more images. So the point being is, the moment you have the bandwidth to deal with data, you will always use it. You can try to reduce it or compress it down, so actually upstream in the detector, but that will just lead to the fact that you read out more images over in the same bandwidth channel, right? So it's not a linearly solved problem. Let's say it like this. So we have to deal with the fact that we have increasing data rates. We have to be able to compress this, write this, and so one aspect that we've been, for example, working on was to increase the throughput on the bit shuffle SF4 compression. Actually, this is just the bit shuffle part. This was done by Cal Cutler from DECTRIS, and this was really, as far as I understand, really a low-hanging fruit that with reducing mem copy and better addressing, and also making it more compatible with new processing architecture. So this is something that also here needs more and more improvement over time, right? Newer architectures need improvements of the compression algorithms. We've heard this many times before, that this is highly architecture specific, right? If you want, you can download it here. Also courtesy again to John Wright from EtherF for the benchmarking tutorial. Yeah, so basically, the only one aspect to deal with this long term is to really reduce the data output, in the sense of questioning what is the data you actually need. Do you really need raw images? When we look at serial crystallography experiments where 80% of the images are actually empty, no hits, does it even make sense to read this out, right? So we are actually driving an effort together with PSI, with Philip Leonarski, Zdenek, you also mentioned him in the beginning, to look into doing some pre-image analysis very close to the detector, not necessarily to stop or to only read out the analyzed or the condensed information, but to give a vetoing right. So for example, that you say only write raw images if you're actually sure there's information in the image that's usable. Yeah? So you may lose, I don't know, 5% of the images that by being maybe flagged incorrectly, but this could massively reduce the amount of data that's actually being generated. Some quite promising results there. Again, here the idea is to use both GPU and FPGA architectures for both indexing, spot finding, also potentially compression, and so on. Obviously, writing to H5 is something that still remains to be a challenge. Yeah? And I think Diego really gave a good outlook how that will limit us. Yeah, so future challenges where we see it, we are working with scientists here. Yeah? So if there's a limit, people will always push it. So even if we reduce the amount of data coming from a pixel, the data bandwidth will always be used. So that's just the reality of it. Bit shuffle LZ4 is great, really great for lossless compression, but I think it doesn't stop there. So lossy compressions, Alexander from DAISY, he really, I think, is doing great work on benchmarking, for example, the effect of lossy compression on electron density reconstructions from MX experiments. It's, I think we really have to look into floating points, maybe where we only need the exponent, and maybe even drop the mantissas. But this must be a community effort. We cannot decide that must come from the scientific community. compression requires decompression. Diego also mentioned that we cannot simply change the way we store images and compress it. This is something that can have massive consequences, install the scientific output later on. So that's something that really needs to be considered when looking at this. Edge computing, I mentioned that, and yes, very, I think I really want to emphasize the last point here. It's really an infrastructure problem. Yeah, the detector is just one part in this entire chain. We generate raw data, but it's really all about making sure that you can actually store this, archive it, transfer it, and decompress it, analyze it at least an equivalent bandwidth. Yeah. So I think this is also, that's it from my side. Yeah, if you have any questions, either now or later, and like Diego said, we're very happy to hear how we can support you guys in trying to push this forward. I think it benefits all of us. Yeah.
So thanks very much for the talk. Do we have questions? Yeah.
Thank you for the talk. My comment would be rather about the DCU system that you are shipping. And when you shipped the first Pilatus detectors, the DCU system were pretty open. And we could imagine, yes, REF did it, change some bits and pieces, for example, to change the compression algorithm that was CBF with byte offset at that time, and fiddle around these kind of things. And with Eiger system, the DCU has become much more closed, and it's really a black box. How does DECTRIS envisage the fact that if we want to put analysis software inside the DCU, because edge computing, of course, is the solution, we need to process the data without moving them. So at ESRF, we have a solution that is not really satisfactory. But beside, next to the DCU, we have another computer that does exactly the same as the DCU. It decompresses the data and does the analysis because we don't want to move the data very far away. So the closest we can do is put another computer just above or below the DCU. So does DECTRIS envisage to open a bit or open the way the DCU system works so that different pieces of software can be run on it?
I can give part of the answer. I mean, the main reason we block the access to the servers is performance. I mean, the systems we have now, they're like 80–90% load already of what they're doing. Anything else installed on it, doing something else, we just cannot guarantee the performance, which is like the main reason that we decided to have a black box from the experience we had from the previous detectors. Because we had quite a lot of performance issues suddenly with people installing additional software on it and not understanding. Maybe this can change now a bit with FPGAs and GPUs, but I think we're currently not at a state that we know how exactly this will look like. Maybe Max, in this direction, you can give some hints. But from our main goal is to really guarantee the performance of the systems, and we're with the current technology also of servers quite at the limit what we can do already. That was the main decision. How it looks like in the future with GPUs and FPGAs, I cannot say. Max, do you have anything?
Yeah, I mean, it is a really good question. So we have the advantage that we can optimize one configuration, right? At a synchrotron facility, you have different users with different needs, with different beamlines with different needs. You have to somehow try to cover all of these aspects and make sure that everybody's happy, right? We can narrow this down and say, okay, this is what we believe is the best solution forward for 80–90% of the users, and optimize this, right? And this allows us to really push the performance to the limit. Like Diego was saying, the DCU really runs at almost 90% utilization in a standard operation. So this is not at peak load, it's really all the time, yeah. So we when you talk about FPGAs, GPUs, yes, we're considering making this partially community accessible. But long term, you have to be aware that we already have lots of FPGAs in each of our detectors. Every module board has, I think, 4 FPGAs on there. So in the long-term vision, you run the processing on the module. You don't even need the DCU anymore. And if that is possible, I don't know how much access is really realistically doable. Yeah, probably 0. Yeah.
Thanks a lot.
Yeah.
Maybe I'll just ask questions.
Yeah, sorry. Yes, go ahead.
Thank you very much. Well, thank you very much for very good presentation. At last, a lot of details. Actually, this info is very, it's really missing from the website for users who really want to know what the detector does. It's great actually to hear even about some problems which you have to face and how you solve it. So if you can make, first of all, available some of this info for users, it would be great, at least on request maybe. But the question is for one of the first slides, like slide number 3, when you have shown the Eiger 16M detector, maybe I missed something or it's just a typo. Yeah, like frame rate 560 kilohertz. Are you sure that it's not hertz?
That's not kilohertz. Yeah,
that's hertz. Yeah.
Oh, okay, thank you.
Sorry, it's a typo.
I just thought it's a new detector which I somehow missed. Yeah,
that would be very wishful thinking.
Not really. If you think about amount of data, but thank you very much. Yes, thanks. That's it.
Thank you for pointing that out. Yeah.
So I'm wondering, when you were saying that rising to HDF5 was slow, have you analyzed performance and have you tried different optimization techniques like page allocation, looking how much you have metadata, can you increase cache size and so on? And we can talk offline about this.
I'm not the software developer of that. I'm a product owner, so I cannot really answer that. Okay. Maybe Sophie is online and could answer this.
Can you hear me?
Yeah.
Yeah. Okay. Hi. So I'm Sophie. I work on FireWriter. I'm a software engineer at DECTRIS. We actually did not play around too much with those parameters. We just felt like to really take advantage of our specific situation where we have everything in memory, where we exactly know what kind of data we write and how our files are looking. We have we first, as Diego said, we looked into the possibility to just not use the HDF5 library at all and write it ourselves, but we realized that's just too much work, actually. And when we found out that we could add this file driver, we tried this out because it was not that much work, but because this is a really nice feature to be able to just manipulate how the data is written. And for now, this was enough for us. For the future, we might have to do some further optimizations. But in terms of, yeah, sorry?
It means users will need to have your driver, right? Or not?
All of this is happening on the DCU. So,
you get the standard HDF5 file. So for the user, nothing changes. It's only for how we write the data into the HDF5. That's the only change. So for users, it's exactly the same as before.
Yes, this is only for writing. You don't need it for reading the file driver.
Just an idea. Would it be possible to have, beside the DCU, simplify a lot the code that is running on the DCU, and once you have done your pipeline with the pixel reordering, flat field correction, and compression done chunk by chunk, dump this directly into a local object store. Could be a Ceph file system, could be a memcached server or things like that, and the DCU just serves the metadata that would allow to build, and we could have on another computer something that is not strict real-time constraints that builds the HDF5 file for the archival, because HDF5 is made for archival, not for online data processing. And those chunks of compressed blocks could be blocks too, because it has already many features that you need. Can be read from other pieces of software, mine for example, and treat them at the same time or even before they are written to HDF5.
So
would this be considered an option for DECTRIS? It also means having some consequent storage next to the DCU, but maybe it's not that much more expensive.
So would you prefer the data to be compressed then or uncompressed? Because I mean, if it's compressed, you have to decompress it at some point.
Yeah, but well, we have a factor 8 in compression for most scattering application. So moving data around, well, we can give the hand to Francesc, who can explain us that yeah, sometimes it's cheaper to compress data and decompress them than moving them. So
okay, I think Max wanted to add something.
Yeah, I mean, that is a very good point, and that's why we actually maintain two data interfaces, right? So we see in this community, we see actually a separation in synchrotrons that have the resources to implement something like you just mentioned, and then we have also a big pool of synchrotrons that have no resources at all for this. And for a big fraction of the beamlines, they're very happy to have archive-ready H5 files, period. Because then they do not have to worry about any of the aspects of how do I correct the images and so on and so forth. The stream interface, I think, would come most closely to what you're actually looking for, because also there we send the data, like the flat field and count rate correction data in the header information, so you could actually reconstruct exactly what you referred to. In this case, you just get it compressed, but like you said, it's in most cases it's cheaper to send it compressed and decompress it again. Yeah, but I understand the use case. Again, it really depends on sometimes even the specific beamline at a synchrotron, if they prefer to go down the road you just mentioned, or if they just want to keep their hands off and say, okay, I don't have the postdocs or the software engineers to deal with this. I need to work with the H5 files and live with the fact that it's lower latency, for example.
So hi, I would like to chime in. I'm Francesc Altet from the BLOS2 development team. Just wanted to say that yeah, BLOS also supports compression in memory, and it supports like parallel compression. So that could be a good fit. And then if you combine this with the nascent BLOS2 plugin for HDF5 plugin, for example, you can store this data right on the HDF5 format without any decompression and compression, right? So just natively you can store that there, and then with the direct chunk access that we are developing, you can access directly this data inside of the HDF5 file, right? So this is a possibility. Of course, it would need to have like this BLOS2 in the pipelines that are using HDF5. But this is just a hint for you that this can be possible.
Okay. Thank you. To the previous question, a quick question. We're referring to that we directly from the server write the data into your storage instead of, so basically it said you can skip your additional server where you need to do something, or was this, did I misunderstand that?
Yeah, I was thinking more that the DECTRIS would provide a second computer with mostly storage on it that could host, let's say, a certain amount of time. Well, now we are limited by the memory of the DCU, but memory is much more expensive than disks. So with good server, you could have offer storage for, I don't know, 6 hours or one shift of data, and those data could later on or during the experiment, but from, let's say, a third computer, being exported into HDFI file for archiving. And yeah, I understand that in the price of the detector, the cost of this additional hardware will be to be added. But your problem is also how can you multiply by 5 the frame rate of your detector and still distribute data to your users. And this path looks like something that is feasible.
Yeah, we have something similar already, which is called the Eiger processing unit, but I guess it's quite old now. So I think it would be worthwhile discussing how this could look like, also together with Plosk maybe. So I think it would be interesting to have an exchange there. So we should have added our emails to the presentation. I guess I can do that and resend it. So the presentation, by the way, will be uploaded afterwards. So if So yeah, anyway, I think we should talk about after the talk a bit and see where this goes.
Yeah, so I mean, there are 2 movements. One is going towards object storage. The other one that we see is towards databases, that people actually put the raw data into single table databases and then extract it after the experiment and archive it back together. So there is some movement in this direction. We don't know yet how we can really be part of that. But yeah, obviously, I mean, the HSDSS, exactly. I mean, that makes sense. Obviously, also making the object store size somewhat equivalent to the image sizes and so on. There's really a lot of potential there to really get an order of magnitude faster. So yeah. Exactly, it's just the wrapper layer. Yeah, exactly. But yeah, it's a very good point. Yeah.
So any other comments or questions from people? Okay, in that case, we can finish up. So thank you again.